I am Sathwika. My roll number is 33. For this assignment, the topic I chose is Powerline Electromagnetic Interference. EMI is nothing but the unwanted noise or interference in an electrical path caused by an outside source. In a more elaborate way, it can be defined as a disruption in an electrical circuit due to electromagnetic induction or external electromagnetic radiation. It occurs when the electromagnetic fields from one device interferes with another device. Effects of EMI. In electronic devices, EMI can disrupt their functioning, leading to errors, data loss, or malfunctions. In communication interference can affect wireless communication signals, causing noise or signal degradation. In power systems, EMI can impact power quality, leading to voltage fluctuations or harmonic distortions. Causes of EMI. Transients and high-frequency voltage spikes, known as switching transients, are produced when power electronic systems and components are switched on and off quickly. Lightning strikes. When lightning strikes near power lines, it can induce high voltage surges in electromagnetic fields that propagate through the power grid, causing interference to sensitive equipment. Radio frequency interference. When external sources of radio frequency signals, such as radio transmitters, wireless devices, and nearby communication systems, can couple electromagnetic energy into power lines, causing interference. Types of power line EMI. Conductor and radiated EMI are two main types of high and low frequency interference. Conducted EMI is defined as interference that uses conductors as a path from source to a receptor. When we talk about conducted EMI, we are referring to noise that is generated by a device or subcircuit and transferred to another device or subcircuit via cabling, PCB traces, power or ground planes, or parasitic capacitance. For example, a motor encoder grounded to a noisy connection conduct noise to the drive encoder interface. The conducted noise would cause the drive encoder interface to receive inaccurate voltage signals, preventing the elevator drive from interpreting the motor speed correctly or drive faults. Initially, it may be assumed that the root cause of the drive operational issues is related to an incorrect parameter setting or possibly a faulty drive interface code. Closer inspection reveals that it is due to the poor grounding of the encoder cable. Radiated EMI defined as interference that uses a wireless path from a source to the victim. This is commonly seen in elevator control panels with AC motor wires are laid in parallel next to low voltage control wiring. The result is coupling between the wires causing disturbances on the data transmission line. For example, if the motor wires were laid in close proximity, the serial link between the PLC means programmable logic controller, and the VFD, which stands for variable frequency drive, the coupling of the signals may corrupt the data packets being transferred between the controller and the drive. Impacts of electromagnetic interference on power quality. EMI can have diverse impacts on power quality, affecting various aspects of electrical systems. A few of them are voltage fluctuations, harmonic distortion, flicker effects. Voltage fluctuations. EMI can lead to voltage fluctuations, including voltage sags, swells, and spikes. These fluctuations can disrupt the normal operation of equipment, affecting sensitive devices and potentially causing malfunctions or damage. Harmonic distortion. EMI can introduce harmonic distortion into the power system, where nonlinear loads generate harmonic currents that distort the voltage and current waveforms. Harmonic distortion can lead to overheating of equipment, increased losses, and reduced efficiency in power distribution systems. Flicker effects. EMI-induced voltage fluctuations can cause flicker effects in lighting systems and sensitive equipment. Flicker is the visible fluctuation in light intensity perceived by human eyes, which can be annoying, cause discomfort, and impact visual tasks. It can result from rapid voltage changes caused by EMI sources. Detection techniques. A few of the detection techniques are as follows. First one is spectrum analysis. An instrument that is used for the analysis of the frequency spectrum of the input signal is known as a spectrum analyzer. It uses frequency domain representation of the RF signals in order to show the relative amplitude level of the signal at various frequencies within a particular range. Spectrum analyzers are essential tools for detecting EMI across a range of frequencies. They can help identify frequency components associated with EMI sources and characterize the spectral content of interference signals on power lines. Oscilloscope. Oscilloscopes can be used to observe voltage waveforms on power lines in real time. They are useful for detecting transient disturbances, voltage spikes, and other irregularities that may indicate the presence of EMI. Power quality analyzers. Power quality analyzers are specialized devices designed to monitor and analyze various parameters of power quality, including voltage fluctuations, harmonic distortion, flicker effects, and other disturbances caused by EMI. EMI receivers. EMI receivers are sensitive instruments designed to detect and measure electromagnetic interference across a broad frequency range. They can help pinpoint sources of EMI and assess the severity of interference on power lines. Field strength meters. Field strength meters measure the strength of electromagnetic fields radiated by EMI sources. They are useful for identifying radiated interference in the vicinity of power lines and determining the intensity of electromagnetic fields at specific locations. A few of the measuring techniques are as follows. The first one is voltage and current monitoring. Monitoring voltage and current waveforms on power lines using specialized instruments can reveal distortions, harmonics, and fluctuations caused by EMI sources. This data is essential for assessing the impact of interference on power quality. Harmonic analysis. Conducting harmonic analysis using power quality analyzers or harmonic analyzers can help quantify harmonic distortion levels in the power system. Identifying harmonic components can aid in diagnosing EMI related issues and implementing corrective measures. Impedance measurements. These can determine the impedance characteristics of power lines and connected devices, helping to identify the potential points which are the first to be attacked due to EMI and assess the susceptibility of the system to interference. Surge testing. Surge testing involves applying high voltage impulses to power lines to assess the system's ability to withstand transient disturbances, such as lightning strikes or switching surges. Surge testing can reveal vulnerabilities to EMI-induced voltage spikes. Surge tests are critical because they are the only tests that find turn-to-turn insulation weaknesses. These weaknesses start at voltages above the operating voltage of the motor and more precursors to serious failures and shutdown of the motor. Such tests are also used to find hard shorts and a number of other mistakes in windings and coils. Grounding and shielding analysis. Evaluating the effectiveness of grounding and shielding systems through impedance measurements and ground resistance testing and continuity checks can help mitigate the effects of EMI by improving the system's immunity to interference. Mitigating electromagnetic interference. Mitigating EMI is crucial to ensure the reliability operation of electrical systems, to reduce the impact of interference on equipment performance, and to maintain power quality. Here are some common mitigation strategies used to address EMI. The first one is filtering. EMI filter. Install EMI filters on power lines and signal cables to suppress unwanted electromagnetic noise and harmonic disturbances. Filters can help reduce conducted interference and improve the electromagnetic compatibility of systems. Shielding. Cable shielding and enclosure shielding. Cable shielding. Use shielded cables for sensitive signal and power lines to prevent electromagnetic radiation and external interference from affecting the transmission of signals and power. Enclosure shielding. Enclose sensitive equipment in shielded enclosures to block external electromagnetic fields and prevent radiation from escaping. Isolation. Optical isolation. Use optocouplers or fiber optic communication to isolate sensitive circuits from noise-prone environments and prevent electrical interference. Transformer isolation. Employ transformers to provide electrical isolation between circuits and eliminate common mode noise. Layout and routing. Separation. Physically separate power lines from signal lines to reduce coupling and minimize the transmission of interference between circuits. Twisted pair wiring. Use twisted pair wiring for signal transmission to enhance noise rejection and improve signal integrity. Shorter trace lengths. Keep single keep signal traces and cables short to reduce the antenna effect and minimize the pickup of electromagnetic. In conclusion, powerline electromagnetic interference poses significant challenges across various sectors, affecting communication systems, electronic devices, and overall safety. Our analysis highlights the sources of EMI, its potential impacts, and the importance of effective mitigation strategies. By implementing advanced shielding techniques, adhering to regulatory standards, and investing in ongoing research, we can minimize the adverse effects of PMI and enhance the reliability of our technologies. Continued collaboration between industry stakeholders, researchers, and regulatory bodies will be crucial in addressing this ongoing issue and ensuring a stable electromagnetic environment for